So we were talking about the simple function y is a function of x, and incorporating the proportionality, let us say that y is proportional to x to the power of n, where n can be greater than 0 and n can be smaller than 0, and n can have many values. For example, if I put n is equal to 1, then this simply becomes the function that we have already discussed. Y is proportional to x to the power of 1, or y is simply proportional to x. The linear system which we have talked about before. But if we have, now I'll make n is greater than 0, n is greater than 0, and n is less than or equal to 1. This is one set that we'll talk about. The second set I have already talked about, and that is n is equal to 1. And then in another case I'll just take up, that is n is greater than 1. May have values 2, 3, 4, 5, 6, etc. And then n is less than 0. So these are some of the functions which we normally have. I'll just discuss some of the salient ones, the important ones. But first of all, if we look into these functions and I take up the x variable and y variable and then plot the graph in which n is equal to 1, which is a linear graph. As x increases, so does y. I'll take specific examples of that and discuss that. But if n is greater than 0 but smaller than 1, then the kind of the function that we obtain, it goes like this. This is n is greater than 0 but n is smaller than 1. As we go from 0 towards 1, then the function changes, some qualitatively only, the function changes something like this. In the second instance, the same, n is greater than 0 and less than 1. For example, n is equal to half. If we instead make the value of n greater than 1, and for example I make it n equal to, for example, 2, n is equal to 2. If I make it n is equal to 3 for the same constant, this rises very sharply, and this I will explain to you later on when I explain to you the differentiation process. And for the sake of the junior students, I'll just put in the differentiation of a function y is equal to k x to the power n. Then dy dx or the rate of change of y, this turns out to be, the constant will remain as such, x to the power of first n, x to the power of n minus 1. Here the n can take any values, and accordingly you can see one thing which I want to place here is that the slope of the curve dy dx, it keeps on changing as the value of x is changed. So the system becomes a nonlinear one. Let us take, for example, y is equal to a constant times x square. Then dy dx or the rate of change of y with respect to x, this is equal to k into 2x, or one can write it simply as 2kx by manipulating the position of 2 and k, 2kx. Here we see that this is again dy dx is a function of dy dx is a function of x, which is not so in the case of y is equal to kx, the linear function. Y is equal to k x, that is y is equal to, if the formula is used, kx to the power of 1, and therefore dy dx, the differential, this will turn out to be k is a constant, multiplied by 1, multiplied by x to the power of 0, which is 1 again. So this is k into 1 into 1 as x to the power of 0, x to the power of 0 is equal to 1. And this we derive, and I want to emphasize and I want you to know, is that, for example, x to the power of m divided by x to the power of n. This is x to the power of m minus n, the law of indices. And if m becomes equal to n, so x to the power of m, whatever, divided by x to the power of m, this becomes equal to x to the power of m minus m, which is equal to x to the power of 0. And since this divided by this is equal to 1, so therefore this number, any number power of 0 is equal to 1. So this turns out to be like this. Okay, so that dy dx becomes equal to k. So dy dx becomes equal to k. And you can see, and this is what I emphasize, that this k is a constant. It does not depend upon y, it does not depend upon x, and so I can say k is not a function of, k does not depend upon the variables of the system x and y. As I said before, this k depends on the system itself. It is the constant of the system, and therefore dy dx is equal to k in this case, but it is not so here. In this case, dy dx is a function of x. As x changes, so does So if I want to plot, or say in this case, if I want to plot dy over dx, this is the rate of change of y with respect to x with x. So we find that this is equal to 2kx. So it again changes in a linear manner. And similarly in other cases we have this kind of function. So if n is less than 0, if n is less than 0, okay, then the function, it goes, x is still increasing in this direction, but y, when the value of dy dx, for example, I take y is equal to k x to the power minus 1. So dy dx, it again changes according to the equation that we have. According to the equation that we have here, if y is a function of x and y can be defined as this, then dy dx is equal to, by the same formula, k into minus 1 into x to the power of minus 1, which is equal to, I can write minus k x to the power of minus 2. Okay, and the dy dx becomes negative, and so in this case the graph goes like this. The graph asymptotically reaches 0 as the value of x is increased. So this is for n is equal to minus 1, etc. Okay, till the value becomes increases and the value becomes equal to 0. Then when n raised to the power of 0, then there is a straight line that we may obtain. It goes like this. I'm just trying to introduce to you, and I wish that you go to the functions in your books of mathematics, try to understand that. But now I go as promised to a system wherein we have more variables than one. Now I take straight away to the case of law of universal gravitation. Universal gravitation, which was derived by Newton, and later on which was verified by the experiment and experimentally verified. Now in this case I have two masses, m1 and m2. There are only two masses. These masses they are staying, and they are at a distance, say r, away from each other. There is nothing else. There is nothing else. There are only three parameters: m1, m2 and r. Being the law of gravitation, and you know that in gravitation two masses attract each other. If this I call 1 and this I call 2, then there is a force of attraction on the mass number 1, and I'll write it as F1, 2, and this is a vector. In the due course of time, sometimes we'll talk about these vectors, and there is another equal and opposite force F21. How do I read F12 and F21? F12 is the force on body 1 due to body 2, and F21 is the force on body 2 due to body 1. And I can say that because the two forces, as they appear to you, they are equal to each other, so I will write that F12 vectorially is equal to minus F21. And if I just take their measure, so you can see that the vector F12 is equal to minus times, because the direction has changed. Vector F21, force on the body 1 due to body 2 and force on the body 2 due to body 1. So I can also write this as F12 vector plus F21 vector, this is equal to 0. That is the net force on the system, because this system has been taken as again an isolated system comprising of two masses m1 and m2, and they may be variables, as also this r, this can also be a variable. So there are three variables in this system. And now what we do is, because the measure of F12, is equal to simply F12. This is not a vector, this is just the measure, the value. And similarly, the measure of F21 is F21, and the two measures F12 and F21 are equal to each other. So F12 is equal to F21, and I can take it as equal to F, say, yani मान लिया. So now there are these four items. One is F, another is M1, another is M2, and there is R. Now we see that if everything else remaining the same, I measure, I'm sorry, don't measure but vary the value of M1, then we find that number one, there is a proportionality, that this F is proportional to M1. Also in a similar manner, if M1 is not changed, only M2 is changed and everything else remaining the same, then F is also proportional to, second feature, F is also proportional to M2. These are simple proportionalities. Okay. Here in the first case I will say that M2 and R. M2 is a constant for this case, as also R is equal to also a constant. These are the conditions. In the second case, I can say that M1 does not change, is not changed, is also a constant, and R is a constant. And there is a third thing that I'll explain to you how it happens, and maybe we end the lecture here, that F is proportional to 1 upon R square, in which case M1 is a constant, does not change, does not vary, and M2 is also kept a constant. So in doing a simple physics, we constrain ourselves that in the first case the variable is M1, in the second case the variable is M2, in the third case the variable is R. Now, why is it that F is proportional to 1 upon R square? This I will just explain to you. Initially, this came as a conjecture, and while Newton was talking about doing things, but today I will ask you to just go through a kind of a thought exercise and establish that F is proportional to 1 upon R square. This is called inverse square principle or inverse square law. Now, a very interesting thing. Suppose I have an sphere. I have a sphere. A sphere with a radius R. And here is at the center there is a point object from where things are emanating in all possible directions. So, for example, something is going out of it. Here there will be a solid angle, all those things, we will not talk just about it, but from an area over here, things are going out. Now this system of an sphere, whatever is going out is spreading and spreading and spreading, and therefore its effect per unit area, because of this cause, it keeps on diminishing. Now, what goes out of here? It goes out in all directions with equal intensity, equal distribution, and so I can say that there is no preferred direction, which means I can say, in other words, that this is secular. Secular. Imagine this secular system. Now there is something which is constantly going out of here and it's spreading in all directions, and there is an effect. Now, I'll ask you, what is the area of this sphere? The area of the sphere is, as you know, as you've been told, that the sphere area of the surface, area of surface of a sphere this is equal to 4 pi into r square, which means that the surface area is proportional to r square. Okay, just like the function y is proportional to x square. So what is the effect? The effect will turn out to be equal to, look here, very interesting. The effect will turn out to be this something which may be per second or whatever, this something which is coming out of the center is spreading out, something divided by 4 pi r square. So this effect, actually now we can say this something is a constant, and so is 4 and so is pi. So this is equal to a constant times constant into constant into 1 upon r square. So that I can say that the effect is proportional to 1 upon r square. The value of the effect is proportional to 1 upon r square. Or I can say with the reverse logic that effect is proportional to 1 upon r square. Now the same kind of a logic can be applied in the case of the Coulomb's law, in the case of illumination from a point object in optics, and here of course in the case of gravitational gravitation, universal gravitation. Now we stop here and I will tell you to learn about something which is called mathematical consistency, and so that, like you know, that the force F is proportional to m1, force F is proportional to m2, and force F is proportional to 1 upon r square. If you take them together, all these variables together, then F will be proportional to m1 multiplied by m2 multiplied by 1 upon r square. Okay, and that is from where we get the condition of the universal gravitation constant, etc., which I'll talk to you about later. Just giving you a direction to try and understand these things, and then we talk more about it, more interesting things about it. So today what we have learned is that if there is something which is going out without, in all directions, or this solid angle which we call, okay, no solid angle, but out of the body surface of the sphere, then we find that, as you can see, there is more which goes out here, and less and less and less as it goes out, and therefore we say that the effect is proportional to 1 upon r square. More about it later, inshallah. Thank you.